Hi guys, you're watching channel Mr. Electron, and these four what you see are high current DC motors. All of them are rated at 12 volts, but we have to find out the maximum current rating. This one you can see the coil inside, how thick the copper wire is, and the commutators. So here I'm going to use this 12 volts 7Ah UPS battery to find out the maximum starting and running current. Running current, as you can see, is around 2 amperes, while the starting current peak is up to 5 amperes. So that's the high current. Now let's open it all up and see how the armature and the magnets look from inside, and if it contains ball bearings or bushes. Now guys, we also have to make a permanent mark because it is going to be difficult otherwise when we close it after viewing the inside parts. So it is open now, and that's the armature. Let's close it up. So guys, as you can see that the copper wires are really thick, and yeah, it's like new from inside, although it looked not so much new from outside. The magnets are also in good condition, no problem with that, and the brushes are also very healthy, okay, and pretty big brushes have been used to carry that huge current. So let's measure the wire thickness. You can see it's almost 1 mm. Now let's place it all back. The wire thickness is 1 mm, no wonder it can carry huge current. So guys, in this video I'm not going to do the motoring mode tests but the generator mode testing. Okay, let's place the screws and keep them held tightly, and also place some WD-40 because it has bushes and not bearings. Okay, and this motor that I am placing WD-40 on, this is the piece I'm going to use for testing. This is a large 1 kilowatt DC motor, and this is a small motor, and this is a double groove pulley which I got from Banggood. Link will be in the description if you want to buy it. And it has like the bolt to tighten up, and it is 8 mm and fits perfectly to the shaft size of the motor. So let's place the rubber belts, and I'm going to use 2 of them because this small motor and the big motor both are going to be under huge load, because I'm going to do the maximum power testing here. So those 2 terminals, brass terminals that you see, to those I have connected 2 wires, and to the wire output I'm going to connect the multimeter pins to measure the voltage it is generating when I run it at high RPM with the help of the large DC motor. This is the DC motor speed controller that I made, and a low high speed and DC socket. So let's do it with 1 belt at the start. As you can see, it is producing around 5.2 volts. Let's increase the voltage. Yeah, its performance voltage has increased to around 9 volts, even 10, close to 12, and we have crossed 12 volts. 13.24 volts was the max we got. Okay, so the output voltage, generated voltage, was pretty good. So here, as you can see, that I've given 2 more wire connections to connect few bulbs and other loads to it. So first I'm going to start with a 6 volts bulb. You see 30 watts 6 volts bulb with 2 filaments. It's from a Royal Enfield. Okay, wait a second, it's moving, and you can see that it is glowing brightly, really bright. And obviously it is really easy for the small generator to light it up, and the voltage is around 7 volts, so the bulb is glowing at its full potential. Now this you are familiar with is 12 volts 35 watts bike headlamp bulb. Okay, so let's connect this one, and this one is also lighting up brightly with a little more drop, as can be seen on the multimeter display. The voltage is dropping. Let's increase it to 12 volts by increasing the driving motor RPM. We have reached around 9.5, 10.5, and we are doing around 12 volts. Yeah, around 13 volts was the max we did. And you can see that I've removed the input supply socket, and it is still running because of the flywheel. Okay, now let's move on to even higher power bulb 90 watts, 100 to 90 watts, 12 volts. Okay, so that has also been connected. This is going to draw even more current, but first we are doing the voltage test right now. Let's see if it can produce that much voltage at such a high load. The load is really big right now for the small generator, and we have reached around 12.5 volts. Yes, the small generator is performing really good, and again we have disconnected the supply and still it is running because of the inertia disc on the driving motor. You see how long it takes to stop because of the large inertia disc. It is really helpful in that. Now enough with the voltage test. Let's move on to the current testing. You can see that I've pointed the meter towards 600 ampere current mode, pointing 0, flashing 0 at the moment. Let's place the multimeter at a point that it is visible pretty good, and the current drawn is around 4 amperes. It is the bulb is drawing. Let's increase it further. We have reached around 5 amperes, 5.5 and 6 amps. The bulb is glowing really bright, and we are peaking at around 6.06 amperes with the maximum voltage of around 12 volts. Here the Starlight 250 watts bulb. This is a really big, it looks small but it is really big. The filaments are really thick. Now I'm going to power up this 250 watts bulb. This is the biggest DC bulb I've got here. You can see that at the lowest input it is producing consuming around 3.5 amps. Let's increase it further. Yeah, we have reached around 4.5 amperes, so somewhat equivalent to the previous bulb, which was 90 watts, and we have reached around 6 amperes. We have crossed the amp rating of the previous bulb. Yeah, 6.27 amps for this one. The amperes were less because that was a 24 volts bulb. Now guys, comes the final shunt resistance short circuit testing. So I'm going to short circuit the wires with the help of an external shunt resistance. Okay, I've given really small loops, and at present at the minimum RPM it is drawing around 5.5 amperes and glowing hot. Okay, it's almost red. 5.5 amperes, increasing the RPM, and we have easily reached around 8.5 amperes and it is smoking red hot. Let's go further and see what happens. Okay, it has caught fire now. That is amazing. Oops, the filament burned out and it broke. The shunt resistance burned out. Now guys, comes the final test for which you all have been waiting, that I said that I'm going to do the maximum power testing. So we have done the maximum voltage testing, that was around 13.24 at the beginning. So now I'm going to go for the short circuit current testing. Now I'm not going to connect any shunt resistance, but I'm going to connect the 2 wires coming out from the DC generator so that it creates a shortest path short circuit. That is what it means. And at the lowest RPM it is producing around 11 amperes. It's the negative sign. Let's reverse the wire. Yeah, and now it is positive and 11 point, yeah, almost 12 amperes. That is pretty good at such a low RPM. Increasing the knob and RPM will easily reach around 20 amps, 22, 23. I don't think the belts can survive more. Okay, so I will have to turn it off, and the peak was around 25 amperes. Well, this DC motor is rated at a max of around 32 amperes. So yeah, the performance was really good. Now the great news is that I'm also planning on making awesome 3D printed designs of your interests, which are going to be available for you to download from the link provided in the description. Now the designs are going to be free to download just for 1 day from the time of upload of the respective video. And I'm going to come with my new projects and new 3D printed designs for like maybe 3D printed vacuum cleaners or more type of battery holders, like who knows what comes to my mind. Hi guys, this is an LED bulb with a power rating of 7 watts, and as you can see, it is broken. Now, unlike the incandescent bulbs. The LED bulbs come with a pre-installed driver circuit. So guys, the first step towards using them as a power supply is to find out if they are working or not. Since none of them are working, we gotta proceed to the next step, which is finding out if the fault is in the circuit or with the LEDs. I'm going to check the LEDs with my old printer power supply with an output in between 30 to 50 volts DC, and here I have 33 volts DC. Since this one is positive, so let's separate it with this red heat shrink tube and start the testing part. Make sure that you have desoldered the driver circuit wires from the LEDs before starting the test. So starting with this one first. Now here we have a dead LED. And we have a perfectly working LED but a dead circuit this time. Because there are no jumper wires in this one, so I will have to figure out another method of doing the test. Take two jumper cables and connect it to the output points of the driver circuit of the LEDs, and then connect the setup to your home socket supply. Next, you have to take a multimeter and move its pointer towards 1000 volts DC mode. After that, connect the multimeter pins to the jumper cables and then turn on the supply. And here we have 88 volts DC, very high. Turning it off. Now guys, I have removed the working LED panel, and let's connect the output of these two wires to this, and let's see if it lights up or not. On close up, we can see that yellow terminal is positive and green is negative. So I'm going to connect it accordingly to this LED panel. Turning it on. Yeah, it's glowing really nice. So this driver circuit is working for sure. Please wear your protective gloves while working on these circuits. The output voltage could be fatal. Now guys, let's test if we can run this big DC motor. It's 24 volts and 16,500 RPM. Turning on the supply. It's not running. Moving on to this gear motor. Whoa! So you see that this motor is running and it's a high torque gear motor. And the RPM is quite high. Now I'm going to try this 24 volts geared servo motor. Turning it on. Oops, it's jammed. And now it's working. Now let's check if we can light up this 100 watts LED panel, and yeah, of course not. Now I'm more interested in this giant LED driver. You see, 75 watts. So we have the driver connection diagram. Black is line and white is neutral. So line and neutral. And red is output DC positive and blue negative, so positive and negative. So let's test the DC output voltage of this driver, and as you can see that it is as high as 126 volts DC, which is very dangerous. So let's test my giant LED this time. Whoa, wow, it works really good. I've turned it off because I have not connected any heatsink. Nice. Now let's do the performance test on my DC motors once again. And now it is working really nice. This power supply is huge. Let's test this CNC motor, 58 watts. Very high speed. And guys, now comes our giant 600 watts e-bike motor testing with a shaft size of 15.8 mm. And guys, as you can see here, it has such a thick high current armature winding. So guys, let's 3D print a pulley for this high current motor. Please note that link for the STL files of the pulley and my 3D printer have been provided in the description. You can check it out. Make sure that you use 100% infill for building a really strong pulley. Now guys, let's see if we can run this big e-bike motor with the LED driver circuit. Whoa, it's working. Super high RPM. And guys, I think you can also power up your angle grinders with it at a little lower and controlled RPM. Now guys, this what you see is a 250 volts DC 10,000 microfarad electrolytic capacitor, very rare. So let's charge it, turning on the supply. And I will have to give pulses because it is going to create a short circuit. Well, I believe it should be fully charged now. Let's check if it is charged or not. Now guys, these what you see are my really old 12 volts 7 ampere hour computer UPS batteries, and here I'm going to use these clips to connect all of them in series. Now if we check the overall voltage, it is only 47 volts DC. Now that's my LED bulb that I'm going to use as the power supply. As you can see that as soon as I connect my yellow negative wire from the LED bulb, the voltage of the battery starts dropping. That is because the circuit is consuming electricity from the battery, which is not desired. Here as you can see, I have this 6 amperes diode. So I'm going to take this negative terminal and connect it to the negative of the diode. Next, I will connect the positive side of the diode, the completely black side, directly to the battery, and this time the voltage will not decrease, and you can see that it is same 47 volts. Like if I remove it, it is still going to be the same 47.28 because it is in the reverse bias condition. So I'm going to connect it like this, and here as you can see that the voltage is increasing rapidly. And here we have reached 50 volts DC. That's quite good. So this battery pack will be fully charged after we reach 56 volts. Hi, today I'm going to do an experiment for finding out which core suits best for the transformers. Now guys, this what you see is a microwave transformer, and this coil that you see is the primary winding of another similar transformer from microwave. I cut off the core and these are the core parts, okay? The next what I'm going to use is a 220 volts to 12 volts UPS transformer. I'm also going to use this 12 volts car headlamp bulb. So without any further delay, let's get started. Take the UPS transformer, and these are the low voltage high current wires. Next, take up your 12 volts 100 watts car headlamp bulb and take one of its wires out of the two and connect it. Now two wires remain, one from the transformer and other from the bulb. Now to these two wires, this microwave primary coil will be connected. The connection is complete. Now next comes connecting supply to this transformer. Now guys, this one is my 220 volts home socket supply. So let's connect it to the UPS transformer high voltage side. Let's turn the switch on. So everything seems fine. The connections are also fine. This bulb, yeah, as you can see that the bulb is glowing a little bit. So next what I'm going to do is connect this clamp meter to measure the current drawn by this core from this. Keep your hands away from a turned on transformer. Now guys, if you look closely to my tester, you can see that the core is actually live. Now guys, at present this meter indicates the current drawn by this core and the bulb, and it's AC current. Now I'm going to try different cores with which either the current is going to decrease or increase depending upon various factors. So 2.34 with no core. Now I'm going to start on with aluminum. Let's see if there is a decrease. Yeah, the current being drawn is reduced to around a minimum of 2.31 because of some impurities, of course. Moving on to the silicon steel laminated iron core, and you can see that the current has considerably reduced from 2.34 to only 1.92. That is amazing. Let's do this way. 1.86, and then the super thick core that I have, and here we have the minimum of 1.64 amperes. So laminated steel cores reduce the iron losses, because of which the drawing current is obviously very low. And not just that, because of the core inside the coil, the inductance increases and so the drawn current reduces. Now ferrite core, here we have 2.01. So guys, the minimum that we have reached with the ferrite core is around 1.89 amperes. So guys, which one of the two do you think is better for transformer core? Silicon steel core or ferrite core? It doesn't matter. If you choose either of the two, you are going to be wrong. Now guys, here I'm going to explain it to you in the simplest way possible, and I am sure that you will understand it and never forget it. Now these two curves are the BH curves that represent hysteresis loss. This one, which is the first one, is for silicon steel core, which is this. Now this piece is from a microwave transformer. I cut it off. So the BH curve area for the silicon steel core is a lot bigger than the curve area for the ferrite cores. Bigger the area means more power loss, more hysteresis loss. So with the help of this curve, we can easily say that the ferrite cores, this one, are much superior to the silicon steel core because of less hysteresis losses. Now B represents flux density and H represents magnetic field. Now guys, we all know that a transformer works on AC supply. So here, as you can see, that at the first cycle, let's say this cycle, which is the positive cycle, the core charges and the field is like this is north and this is south, and then it goes to the negative side, which removes the north and changes it to south here, and remove the south from here and changes it to north here. Now comes case 1. Let's say that this core is silicon steel type core, and the AC supply that we are feeding to the primary is from a high speed switching supply, like very high frequency. But the core that we are planning on using is the 50 Hz or 60 Hz transformer core. So the hysteresis loss is going to be 2000 times more than usual, resulting in heating up your silicon steel core to insane temperatures. So for these very reasons, steel cores are restricted to be operated at lower frequencies of 50 to 60 Hz, and for higher frequencies even up to megahertz, ferrite cores are used. Now guys, if we consider case 2, another type of power loss will occur, which will be due to saturation. Now here, as you can see on the diagram, here I'm using a ferrite core. You see it's like the D type, this type. You see, somewhat similar I tried to make. Okay, that's your secondary, and this one is your primary number of turns, D type of ferrite core. So when the primary is fed with low frequency AC supply, which is 50 Hz, the ferrite core reaches the saturation point very easily. Here in the diagram, as you can see, that the induced magnetic field is inside the core, the D-shaped core. Now because the frequency is very low, 50 Hz, it gets saturated, the core gets saturated very easily. And by saturation I mean that the core gets fully magnetized. Now even if I increase the current from the power input source, it is still not going to get any more magnetized, and that induced magnetic field which was inside the core gets
out of the core, which is called the popping effect, and hence it draws huge current from the source and creating large amount of power loss.
Now guys, I'm going to share with you a very important pointer, another one, and I'm going to make you understand that with an example of inverters. Now this big, large, heavy inverter is 600 watts, but this very small mini inverter is 1500 watts. Although it is really small, but still it is 1500 watts. And this one is so big, but still it is only 600 watts. Even though both are modified sine wave inverters, but still, why is that? This inverter has high speed switching frequency mode because of the ferrite core type of transformer, while this has the old one, laminated steel, silicon steel core type of transformer, and that transformer is so heavy that it makes this inverter not portable at all. But this is like very easy to pick up. This is so heavy that this is the super big transformer of the old type of inverter. And now guys, I've also opened this small size high power inverter, and you can see the transformer size is just this much. You see, it is really small, and yet it is capable of handling up to 1000 watts. That is because it has two stages. You see, this one is so big. So now we can say that the ferrite cores are much better than the silicon steel core. Again, no. What will you say for the motors, the low frequency operating induction and universal motors? You cannot use ferrite cores because they are brittle. If they fall or get a jerk, they are going to break, which is not the case with the silicon steel core. These motors operate at around 50 to 60 hertz, which is low frequency, that is really bad or creates excessive loss for ferrite cores. So guys, I tried to cover every possible pointer for the ferrite cores and the silicon steel cores. I believe that now you have a better understanding for both of them. And if you really like the video, you can contribute by subscribing to my channel, and then you can get notified for the upcoming awesome videos. That's it. See you in the next one. Bye bye.